All right, so we have another interesting Lagrangian mechanics problem here. This is a rotating loop of wire, okay, frictionless, of course, and this is not a string here. It's just a line pointing from the center of the loop out to this massless, or this, I guess it has a mass, this frictionless bead that is allowed to roam freely on this loop of wire. Now we're going to give it a twist. We're going to just have this wire rotate around about this axis right here at a constant angular velocity omega. And we're going to solve for this, and the question is basically, are there places of stability or equilibrium points, right? Points of equilibrium for this bead on this wire, and if so, are they stable? And if they're stable, what are the, if the bead's going to be trapped there and given a small displacement, it's going to oscillate. What are the frequencies of those small oscillations? So, start off with our Lagrangian, the kinetic energy minus the potential energy. Okay. And let's see what we have here. So, a couple ways you can set this problem up. The way I'm going to do it is go into, so rather than dealing with the motion of this bead around this axis and all of this, what I'm going to do is go into the frame rotating with the hoop. Okay, so in that case, we can just look at this as a still hoop, all right? Just a normal two-dimensional type case, right? Except we'll also account for a centrifugal force. So basically, we could just picture a hoop standing still with gravity acting on it, everything like that, except there's this pesky weird force that depends on this distance from the axis. All right, so just a weird force that shows up once we're in this rotating frame. Okay. All right. So let's see what we can do here. So in this rotating frame, for kinetic energy, is constrained just to move around this circle. So I'm just going to have a 1/2 m. Let's call the length of, or the radius of this hoop A. So we're going to have an A theta dot for our velocity, and that's going to be squared. All right, so great. For our potential energy, let's go ahead and we'll have gravitational potential energy, but then we'll also have this weird potential energy that comes from this fictitious force. Okay, so let's just do gravitational real quick. It's much easier. All right, so we're just going to have a minus mg a cosine of theta. All right, so what I've done is just defined my zero right through this point in the center of the hoop, and all of our potential energies down here anyway are just going to be negative, and above that will be positive. Okay. Now we need to find our I'll call it V sub c, which is the potential energy due to the rotation. All right, so this is going to, if we were to switch back to our fixed frame, we see the bead, if it's in one spot, is just going to be going in a circle. So the force So the force is that's making it go in a circle is going to be equal to its mass multiplied by the acceleration for a point going in a circle, which is just v squared over r, or we can write that as m. I guess here. All right, so r is going to be a. Well, let me write this this way real quick. Mr omega squared. So v is just so r here is the distance from the axis. All right. Okay. But that's going to be equal to m. All right. The distance from the axis is a sine of theta. Okay. All right. So I think we're good there. Okay. Then, so let's keep looking at this in terms of r here for a second, because when we want to go from a force to a potential, as long as it's a conservative force, et cetera, right? What we do is we integrate and throw in a minus sign. So we're integrating with respect to this thing that's changing, the position, r, right? So going, that's where we get an mgh potential energy from a minus mg force. All right, we integrate by the distance, and we get the h. All right, so here we go. So we're going to integrate this with respect to r. So I'm going to write a 1/2 m, then we get an r squared omega squared. Okay, and now we're going to just put in our a sine of theta for this r. Okay, so 1/2 m a squared sine squared of theta omega squared. All right, I think we're good now. So we have two pieces for our potential and one piece for our kinetic energy. So I'm going to go ahead and write the Lagrangian here, right? So T minus V. Our T is equal to 1/2 m a theta dot, and these are squared. Then we'll minus these parts off, so we actually get a plus mg a cosine of theta. All right, and a minus of this minus 1/2 m a squared sine squared of theta omega squared. Here's our Lagrangian. And we only have one generalized coordinate, which is theta. So we only have to do one equation of motion, one Euler-Lagrange equation. So I'll write out the Euler-Lagrange equation real quick. Oops, getting sloppy. With respect to theta dot, partial derivative of Lagrangian here, minus this is equal to 0, partial derivative with respect to theta. So finding some of these pieces. With respect to theta dot, here's the only theta dot in town. So the 2's gonna cancel out this 1/2. We'll have an m. This a is still gonna be squared, and then we'll have a theta dot like that. Okay. And hey, while we're at it, let's go ahead and take the total time derivative of what we just found. All right. Which is just ma squared theta double dot, because m and a are constant. We'll take the partial derivative of this with respect to theta. All right, so here we are going to have the derivative of the cosine will just give us a minus sign. So minus mga sine of theta. And then here we have a minus ma squared omega squared and then we'll have a sine squared multiplied by the derivative of sine squared, which is just cosine. Right. So this sine squared goes away, and we just have a sine cosine. So here we go. Moving this over here and making it positive, we just have to set this equal to this. Ma squared theta double dot is equal to minus mga sine of theta minus ma squared omega squared sine of theta cosine of theta. This is our equation of motion. All right, and let's go ahead and write this a little bit prettier. We're just going to divide by ma squared and bring things over to the other side. So that just gives us a theta dot. We'll bring this over, we get a plus sign. We'll just get a g over a sine of theta. All right, and now a plus sign again. We divided by ma squared, so that part goes away. We just get omega squared sine of theta cosine of theta equals 0. So here's our equation of motion. And as a side note, our Lagrangian does not depend explicitly on time, and our potentials are neither one of these pieces of our potential energy depends on a velocity. So there's no theta dot in these. So that will tell us that the energy of this system is conserved. All right. Yeah. So yeah, we won't go through that here, but I don't know. Maybe we'll do it in a different video. All right. So the energy of this system is conserved. All right. So now let's look at the equilibrium positions. So for equilibrium, theta double dot will equal 0. So this tells us that g over a, sine of theta plus omega squared sine of theta cosine of theta is equal to 0. So there are two ways for this to happen. One is sine of theta could be 0, okay? All right. Or we could have g over a plus omega squared cosine of theta equal to 0. So here we get, for this one, theta could equal 0 or pi. All right, so this makes sense, right? You know, this an equilibrium point here, right? This one looks obviously like it's going to be stable, at least for some values of omega. And the equilibrium up here doesn't look like it's going to be stable no matter what. All right, but those are our two equilibrium values. All right, or what we have, let me just double check, make sure I hope I didn't get a minus sign problem in here. Okay, so I found a mistake. And it comes back to when I was doing this little centrifugal potential thing. I integrated, but I forgot the minus sign. Remember that the a conservative force is minus the gradient of a potential, right? So when we go backwards and we integrate to get a potential from a force, we need that minus sign there. I think I said it, I just didn't write it. All right, so then This messes everything up, of course. There should be a plus sign right here, which would give us a plus sign right here, a plus sign right here, okay, and a minus sign right here, which gives us a minus sign right here and a minus sign right here. Okay, I think I've got this stuff fixed. All right, so again, we have equilibria positions at theta equals 0 and pi. And now we are going to solve for the theta here. So what we do is we bring this over, divide by, so we'll have a g over a. We're dividing by omega squared, right? And then to get theta, we have to take the inverse cosine. All right, so here we go. All right, so one thing to note, though, is that this is not defined, right, for values greater than 1. All right, so this tells us, and yeah, by the way, A is positive, G is positive, so we're not worried about negative. All right, so we're going from 0 to 1. So that means that G over A omega squared, well, it's going to be between 0 and 1. All right. In order for this solution to work out, and basically in order for there to be this third equilibrium point. So there will always be equilibrium points at theta equals 0 and pi, right? The top, or the bottom and the top of this ring, there will always be equilibrium point. Whether or not they're stable is a different question. But only when this condition is satisfied will there be a third equilibrium point. All right, so maybe we can write this in a different way. We won't worry about this 0 condition. All right. So in order for this to be less than 1, we have a G over A. All right. It has to be smaller. Wait, let me just double check this. All right, so I think so omega has to be larger than the square root of G over A. Double check that just to make sure. So yeah, I think this is correct. Maybe another mistake here, but let's see. All right. So let's dive into the frequency of these small oscillations. Let's work with this case first. So what we have here, so for theta really close to 0, what can you do? And for theta really close to pi. All right, so for theta really close to 0, sine of theta is going to be about theta, and cosine of theta is going to be about 1. Okay? For theta really close to pi, sine of theta, so we've gone up and over the hill, and now we're coming back down, right? So it's the same as before, except now the slope is the other direction. So this is going to be roughly equal to minus theta. And cosine in that same amount of time has switched sign, and it's now about equal to minus 1. Okay, so let's do equilibrium at theta equals 0 first. So here's our equation, and we're just going to plug these guys into here. All right, so we have a g over a. Sine of theta is about equal to theta. I'm just going to move this over to the other side and make it positive, so we have an omega squared. All right, so, and here, sine of theta, did I make yet another? Oh, I'm using the wrong equation. Sorry about that. Right, this is an equation where we're saying equilibrium, but we're looking for the oscillation, so we need to use the full-on equation of motion. All right, so all I have to do is put a theta double dot right here. Okay, I think we're good now. All right, so this is about equal to theta, and this is about equal to 1. So here's what we've got. All right, so if I write this in the form of the simple harmonic oscillator equation, all right, so here we go. This is equal to 0. So it's either going to blow up or oscillate. So if this term in here is positive, then it's going to oscillate. If this is negative in here, it's going to blow up, and the equilibrium is just not stable. So so for all right, let's write it out. G of A minus omega squared greater than 0. This tells us that omega is less than G over A square root. Okay. Right. This is going to give us stable equilibrium with oscillations. Let's use a different symbol rather than omega. Let's just say frequency, whatever. Frequency of small oscillations is the square root of this piece right here. So G A minus omega squared square root. Okay. All right. Now, so if G over A minus omega squared is less than 0, which is to say that omega is greater than G over A under square root, then then this part is negative, right? And we're no longer stable equilibrium, so it's unstable. Okay, so just to get some physical intuition here, what we're saying is that there's this critical angular frequency of the square root of G divided by A. All right, so it depends on the strength of gravity. So the stronger gravity is, the faster you have to twirl the thing, or vice versa. The smaller the radius is, the faster you have to twirl it. This all makes sense if you actually think about this rotating. If you're below that magical critical frequency, then the stable equilibrium point is going to be right here, okay, and any small displacement will just cause the little mass to oscillate back and forth like this. Once you get up past that point, then this is unstable, so the mass will fly away to some point on this, which we will talk about later, with this angle right here. Okay. There's also this equilibrium point up here, which let's show that that is unstable no matter what, no matter how fast we're twirling this thing. All right, so to do that, we're going to look at this theta, this second case right here. Okay, piece of paper. Okay. So rather than equilibrium at theta equals 0, let's do equilibrium at theta equals pi. Okay, so now what we're going to do, go back to our full-on equation of motion right here and plug in these values. Okay, so we have a theta double dot plus g over a. This time it's a minus theta right there. Okay. Minus omega squared. Sine of theta will give us a minus theta, and cosine of theta will give us a minus 1. Okay. So let's just rewrite this real quick. So we'll have a minus g over a, and then these minus signs will cancel out, but we'll get our minus omega squared like this. Okay, so now this term in the parentheses, this has to be positive in order for us to have a stable equilibrium. Can this be positive? Well, it can't, because g is a positive number, a is a positive number, omega squared is a positive number, and we have these big fat minus signs right here. So, sorry folks, but once you have a minus sign out front, g of a, so we're factoring out this minus sign like this, this is always going to be less than 0, unless you can flip the sign of gravity, okay, have some weird imaginary rotation or negative curvature on your, yeah, anyway, don't worry about it. This will always be unstable for our situation. So that takes care of our two equilibrium positions, relating to this condition right here. Okay, the one up at pi, this one and this one, this is always unstable, right? There's no way you can stably balance a bead up here on this frictionless hoop, and if you perturb it slightly, it's not going to go back to its place. It's going to get further and further away, and it's going to fall off, right? The one down here, that depends on how fast we're spinning the hoop. If we're not spinning it too fast, then the bottom is stable, all right? So not spinning too fast is meaning our angular frequency of the hoop going around is less than the square root of g over a. If we're spinning it too fast, then it's going to be unstable, in which case it will not only fall off the top, but it will also be thrown out from this bottom. All right, so now let's talk about where it's going to go. We found this third case right here. All right, and look, this is only a case of equilibrium when omega is greater than that magical critical angular frequency. All right, so now let's see if we can find the frequency of oscillations around this. So again, this is only for angular frequencies above this critical frequency. All right, this gets a little bit tricky. I'm gonna have to keep an eye on my notes while I do this, so I don't make too many mistakes. All right, so what we're going to do is basically a Taylor series, all right? Because we're not, yeah, anyway, we're at this other angle now, which we don't know what it is. All right, but we're going to perturb it slightly so we're at some small displacement from this angle. Okay, so this angle here is going to be this angle here. And then phi here is really, really small. All right, so if we do a Taylor expansion in phi here, we'll just keep the first term. So we have a sine of theta plus phi cosine of theta. Okay, and a cosine of the same thing is going to be about a cosine of theta minus phi sine of theta. Right, so there's your derivatives, and anyway. All right. So now let's go ahead and we're going to plug theta plus phi into our equation of motion. You know, let's call this theta naught, like this, just so we know it's a position out there, right? All right, so that's going to be this guy. All right. Okay, we're going to plug this into here. All right. The reason I call it that, anyway, it's a constant. So when we take the double derivative of it, that will go to 0 for that part. But phi is not a constant. So when we take the double derivative of this, this part goes away, and we're left with phi doubled up. Okay, plus g over a. Now let's plug in for sine. Sine of theta naught plus phi of cosine theta naught. Okay, now let's plug in minus omega squared. Now we're going to plug in both of these guys. Multiplied, this is just multiplied, so cosine of theta naught, phi sine theta naught. And this is all equal to 0. And we're going to throw away the term here that would be phi squared. Just so unimaginably tiny. We're not going to worry about it. Okay, so what we're gonna do real quick is use an identity on this thing. Well, first let's kind of break things up a little bit. Let's go plus so the identity we're going to use, so we just have sine squared x plus cosine squared of x equals 1. Okay, so we're just going to replace this sine squared with a 1 minus cosine squared theta naught. So let's go ahead and write this out again. G over a sine theta. So kind of the goal here is we just want as many cosine of, I can't write and talk at the same time. As many of these cosine of theta naughts as we can, because now what we're going to do is plug in this right here, or in other words, anytime there's a cosine theta naught, that's going to be equal to g over a omega squared. So let's go ahead and plug those in. All right, and we might be a little concerned about this sine of theta naught, but we'll see that that goes away. So now we're plugging this in, so we have a g over a omega squared. Okay, so a minus omega squared sine theta squared, and now we'll plug in our g over a omega squared. Put this one right here. Plus omega squared phi 1 minus 2 g over a omega squared quantity squared equals 0. All right. So so one thing to note, here we have a g over a sine, and here we have a g over a sine, and there's a minus sign here. So both of those will go away nicely for us. So let's go through and simplify some things. G squared over a squared omega squared phi. And then we'll have a plus omega squared phi minus a 2 g squared over a squared. And this omega squared down here will cancel with this one up here, and we won't get an omega to the fourth, we'll just get omega squared. All right, now we see, oh yeah, there's a phi with this as well. All right, so this will subtract off this one, so we can just get rid of that 2, and we just have one of these guys left. So here we go. So here we go. All right. And again, this must be positive. Just make sure I did this right. This must be positive because we are at a frequency above that critical frequency. So, so the equilibrium is stable with frequency of oscillation as omega squared minus g squared over a squared omega squared, and all under a square root. Okay, so let's just sum up real quick. There will always be 2 equilibrium positions for this problem. Okay, one of them is always at the top. It's always unstable. All right, never mind. There's always, all right, there's either 2 or 3. Okay, but there's always one that's stable. Okay, I lied. All right, this one's always there. It's always unstable. This one is always there, but it's either, if it's stable, then those are the only two equilibrium positions, top and bottom. If this frequency becomes larger than that critical frequency, which is square root of g over a, then this equilibrium position becomes unstable, and another equilibrium position appears at this special angle, which was that inverse cosine thing. All right, and that one is stable. Okay, and so here's the frequency for that special angle if we're above the critical rotation angular frequency, or angular velocity, I guess. All right, and then here was the frequency for oscillations about the bottom of the ring if we're below the critical